What is up YouTube? Welcome back to another episode on Code with Ani. And in this episode we're going to take a look at how we will calculate the time complexity for a given algorithm. Okay, so I'm going to show you how the time complexity such as O of n square or O of n is calculated programmatically, right? I'll write a program and I'll show you how you can calculate the complexity of that said program. Okay, for this video we're going to take a look at one of the basic sorting technique. Okay, so what I intend to do is I have a list of integers, let's say 1, 12, 3, 9 and 31 for example. My end result is an ascending order sorted result, okay, which is 1, 3, 9, 12 and 31. So this is my expected output. This is going to be my input. So I'm going to write a custom sorting technique, or without using any of the library code, I'll show you how you can sort the elements and then we'll calculate the complexity taken by that particular algorithm. Okay, so let's we have a package here, dsalgo. Let me create a class here called okay, I'm not able to see, yeah, Java class. We call it simple sort. Okay, and what we'll do here is we'll try to write a method here, public. It's going to return me sorted integer array and just call it sort, and this is going to accept an array of integers. Okay, and what I'm going to do is I'm going to iterate over the elements of this array. So I'm going to say array dot for based on index based access for I equal to 0, I less than array dot length I plus plus, and for j equal to I plus 1 or int j equal to I plus 1, j less than array dot length j plus plus. What we'll do is if array of I is greater than array of j, basically if I find an element which is greater than one of the elements in the array, I'm just going to swap their positions. I'll show you with a dry run what I'm intending to do. I'm going to swap it. So I'm going to say int temp is equal to array of I, basically going to write a simple swap. This is called as a simple swapping technique. Array of j, temp equal to array of I is equal to array of j, just replacing the values in the positions of I and j, and array of j is equal to temp. So what this basically does is stores the value of array of I into temp, and it will assign array of I with what is there in array of j. That position, whatever is the value there, it will get assigned to array of I, and then array of j is assigned whatever was stored in array of I initially, which was in temp. So that's the reassignment here. So this is a simple swap technique, and what this for loop basically does is this two for loops do is this will start iterating. Let's say we have elements 1, 3. What is the element list that I had there? This one, right? So let's take this and put it in simple sort here, and what this will do is it will take the first element 1 based on this for loop. I of 0, array of 0 is basically 1, and for every other element from I1 to length minus 1, less than length, right? So you'll all the way up to 31 because array starts at 0. So we'll take 1 and we'll compare it against 12, 3, 9 and 4, and we'll see if 1 is greater than 12, no. 1 is greater than 3, no. Neither is it greater than 9, nor it is greater than 31. So this if condition will not be executed for any of these because 1 is less than all of them, not greater. Likewise, we will move to 12 next based on this for loop, and then we'll compare against 3, 9 and 11 based on this for loop, and we'll see 12 is greater than 3, yes. Then we'll do a swap, we'll put 3 here, we'll put 12 here, and then again we'll compare 12 with 9, and then we'll swap again the position of 12. 12 would now be sitting here, it will get swapped with 9, and 12 is not greater than 31, so that ends this if condition here. Basically this will not execute, and then we'll move ahead with the next element. So likewise, by the end of these two for loops, we will have a completely sorted list of elements here, or array of elements here basically. So if we were to calculate the time complexity of this one, let me just return the array here because this is the sorted array now. it's an in-place sorting, so the array will be the same array that we got as input, just the positions of the elements would have changed here. We just return this array back, and let me try to execute this code and show you. Say int, let's create an array, new int of, okay, let me create some elements here, the one that we put there in the comment, 9 and 31. All right, now we'll say simple sort space simple sort is equal to new simple sort, just creating an instance of the simple sort class, and we're going to say dot sort, and I'll just pass the array, and the response I'll store it in the result. All right, and we'll simply say result dot, we'll just print out the elements of result. So result dot for every element, just say system dot out dot print, not print line, I'm not going to leave a new line here, just gonna print out the value of I and just leave a tab space. I'm just gonna say /t. So just print out each element in a single row separated by space. Okay, so this is how it's going to print out. So let's see what is the result of this one. If the algorithm works as we intended to, let me run it. Since this is a Gradle based project, it is building the Gradle dependency first, and then it will start the Gradle daemon, build the project, and then it will execute this code. And we should be able to see this outcome that we printed out here in this comment. This is what the print line statement should also reveal to us. And then we'll take a look at how the complexity can be calculated for this algorithm, which is a simple sort technique. So if you observe here, the algorithm runs from I equal to 0 to up until the length of the array, which is 5. So we'll go from 0 to 4 because this is a strict less than. And the result is out here. You can see 1, 3, 9, 12 and 31, which is the sorted ascending order sorted array. Now this runs from 0 up all the way to the length n-1. If n is the length of the array, it will run all the way to n-1, 0 to 4. And let's approximately call it as for larger inputs of n, let's say the n-1 will also be approximately n. And here as well, it runs from i+1 to n-1. And for very large inputs, this is also approximately equal to n, right? So for each element I, this is executed n times. So for n elements, this will be executed n into n, which is n square times. So understand this simple concept, a for loop, and there is a for loop inside. So you will just multiply the values of n. You will just approximate this to n times execution, and this will also be an n times execution, and we'll say approximately it runs n square times. Okay, do note that this if condition is executed in O of 1 time. Basically what I mean by O of 1 is it just takes a constant time to swap these elements. Okay, this does not contribute much to the algorithm, because for n square times this running, this is going to, for n number of elements, right, even if there is very large input, this swap is only going to take O of 1 time. So this constant doesn't matter. So at the end of the day, this algorithm's time complexity is basically the complexity taken by these two loops. And because there are nested loops, and as many nested loops as you go in, just you have to multiply the values of n. So if there are 3 loops, it will be O of n cube. And now there are 2 loops, it's going to be O of n square. So that is the time worst case complexity taken by this particular algorithm, because assume that in the worst case scenario, the array that I provided is completely in descending order. In that case, for every element, there will be a swap that will be executed, right? Like in this case, we skipped the swap for 1 because 1 is the smallest one, and coincidentally that is present as the first element. But imagine if this was a descending order array, it will be executing this swap for every single element out there. So the worst case time complexity for n elements is going to be O of n square, because there are 2 for loops that are running. And this one starts, and this one has to execute all the way from i+1 to n-1. Again, it will go to the next one, and then it will execute again some n-1 times. So yeah, this is how the complexity is calculated for a nested loop, and this is how complexity is calculated for an algorithm as well. Okay, Now if this was a single for loop, it will be O of n, which is also called as linear time. O of 1 is called as constant time, because that's what the time it takes for swapping two elements. I hope this video was quite helpful to you guys. If you liked it, hit the like button, subscribe to Code with Ani if you haven't already, and I'll see you guys in the next one with some more examples of algorithms, and we'll also delve deeper into data structures. Until then, see you guys. Bye bye.